to convince yourself there is a mistake, you let me know. So my acceleration is that. That is my displacement. And my case is a little bit different. It should be a lowercase k, whichever style points I'm going for. It's the same k. This is the same k as that.
Is that minus?
Is that what?
Is that minus n?
Yes, it is. Let's simplify it. So a's cancel out. Sine omega t cancels out. I'm left with negative, actually the negative signs cancel out. So I'm left with k. My spring constant is equal to m omega squared. Which tells me that omega is equal to the square root of k over m. So if I know the spring constant and I know the mass, I can predict what the angular frequency is. I know that the period is equal to 2 pi divided by omega. So that becomes 2 pi times the square root of m over k. Since we're divided by omega, it gets flipped. My frequency is 1 over my period, and that's going to be equal to 1 over 2 pi square root of k over m. But square root of k over m is just omega, so that's equal to omega over 2 pi, which matches what we got here. Or omega is equal to 2 pi times the frequency. Your textbook uses 2 pi f. Wherever I have an omega, they use 2 pi f. That's where it's coming from.
So for the test, if we have what's frequency again? Is it cycles over time or time over cycles?
For which one?
For frequency, is it time
It's
over
cycles per second.
So if we
Or
have
per time.
So if we have those two information, we could just multiply by 2 pi to find the angular velocity.
Wait, say that again? If you were given regular frequency, yes, you multiply times 2 pi to get the angular frequency.
Okay.
Or the hypothetical virtual angular speed of a wheel that's spinning.
Okay.
So what can you do with it? Well, conveniently, you know those masses and the slinky I was looking for? That Sasson was using. So if I take this spring right here, let's actually do something with numbers. It has a certain height to it when it's just sitting there. And so I can just put it on my meter stick. I'm going to use the red indicator. So it is at an initial position of 45.7 centimeters. That's the initial position. I'm going to add a 200 gram mass to it. And so I need to know how much the spring has stretched. And that indicator is now at, it's like 30.8. That's my final position. So what is my displacement? is built into this, and this is an assumption, the fact that my initial position was higher than my final position, and the initial position value is greater than my final position value, and the way I had my meter stick, 0 is at the base. I sort of forced in up as positive. So I have my displacement. The force exerted on that mass is pointing upwards, because that displacement is downwards and the force is in the opposite direction. I know that the spring force is equal to negative K delta X. So I have negative K delta X equals, well, in this case right here, if it's just hanging there in equilibrium, what's the force downwards? So I can find my spring constant. K is equal to negative mg over delta x, which is negative, I think that's 200 gram mass, 2 kilograms times 9.8 meters per second squared, divided by my displacement of negative 0.149 meters. And we end up with
-4.67,
negative 4, it shouldn't be negative, I got 2 negatives there that cancel out. So 4.68
yeah.
units.
Newtons per meter. Can you,
Kilograms over?
What were you saying?
Kilograms over second? No, seconds, meters? Oh, second squared.
Yeah. So Newton per meter, which is the more traditional way of writing it, or 4.68 kilograms per second squared, is also legitimate. So if I put a 100 gram mass on there, what would be the position of the red indicator?
Wait, I have a question.
Yep.
We never converted our centimeters to meters for this equation.
We did?
I
Okay,
did
we
there.
did it for.
So if I put a 100 gram mass on it, how much would the spring stretch? What'd you get, Margaret?
6.58.
That seems a bit excessive.
100 gram, right?
Yeah.
So that's 0.1 kilograms?
Yeah.
That's what I did.
So we have K. K is not gonna change unless we change some aspect of the spring, which we're not. So I have 4.68 times delta X is equal to 0.1 times 9.8.
Yeah.
0.209.
How'd you get that?
Multiply
I
0.1
did.
by
Divided
9.7.
by 4.
And then I divided by
Okay, I don't know what I did the first
4.68 because it's our
Okay.
spring constant.
Oh, I divided by 1.149.
209 doesn't seem right.
Is it supposed to be negative?
I think I got,
Okay, it will be a negative, but,
I think I got 13.15 for the spring constant.
oh, you do not get 4.68?
I mean, unless I just,
Boy.
is 0.2 times 9 point, because the negatives are gonna cancel out, so
Oh, yeah,
0.2 times 9.8 divided by 1.49.
I got 13.15.
I thought that was 0.21. I see now.
That's 0.2.
Yeah, I see that's a K now. 0.2 times 9.8 divided by 0.2.
That would make sense at something bigger than 10.
Yeah, it's 13.15.
All right, so
So our displacement is negative 0.075 meters.
Which makes sense. If I have half the mass on there, in other words, half the weight pulling down, then it shouldn't stretch half what it did before. Well, it stretched almost 15 centimeters before with half the mass on it dangling there to go about 7.5 meters. Let's find out how close we are to that. That's a 100. That red indicator, is that 40.9? So X final 40. .9 meters, and so that is a stretch much less than what we predicted.
Did you measure from the base plate to begin with?
Thank you. I did not. It's like 38.6. And so that would give us a displacement of whatever that difference is.
7.1.
So it's 7.1,
Yeah.
and we had predicted 7.5. Not perfect, but it is what it is. So I now have this sitting right there. If I pull it down and let go, it'll oscillate back and forth. Which should not have been a surprise to anyone. The question is, what would we predict to be the period of that oscillation? Let's figure it out.
I forgot the centimeters.
I forgot the centimeters.
38.6
Oh,
minus 1.
actually that'd be -2.
Are you serious?
On 10-point problem? Yeah, wrong units.
That's a lot.
Yeah. It's not math class, it's physics. That was bad, I should have looked at that, it's at 38.6 meters. Well, I'm under 2 meters tall, so I know that can't be right. All right, so let's predict what that is going to be. I know that omega is equal to the square root of k over m, which is the square root of 13.13. 15 newtons per meter, divided by my mass of 0.1 kilograms. Units?
Meter per radians per second.
Yep. Radians per second. My period is going to be 2 pi divided by omega, which is 2 pi divided by 11.467. That's 2 pi radians over 2 pi 11.467 radians per second.
.58 seconds.
Let's find out how close we get. So I'm going to pull it down. So that, right now, the indicator is at 38.6. I'm gonna pull it. Pull it down to 36, and then I'm gonna let go. I need people timing.
Okay. Ready?
3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
4.99.
Same.
Yeah, I got 5.01.
I got 5.99. I might have started it a little too soon.
You had 5.99.
Yeah, I think I probably started it too soon.
Anyone else? Let's do it again, since apparently your mind reading skills are a little bit off this morning. Although the 5.99 is closer to the prediction. All right, which doesn't necessarily make it right. All right, so rolling down to there. All right, 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What do people have?
5.80,
5.9.
I have 6.09.
5.85.
5.85.
Did I miss one?
09, but 6.09.
All right, so our average?
$5.9275.
5.9275. That's for 10 oscillations, and so it would be 0.59275 seconds per oscillation. That would be the period. We predicted 0.58. We got, so we're off by under 2%. Questions to hear?
That was pretty close.
Yeah. I'm about to do one that's not gonna get close, and then the question is why. However, it's not why am I doing it, but why is it not close? Keep putting it down somewhere. Oh, here are both of them. If I were to model that equation, I know that it got pulled down to, I was trying to pull it down so that the red marker was at 36 centimeters. So my amplitude is from wherever its equilibrium position is to where I pulled it down. That's the equilibrium position. I pulled it down to 36, so my amplitude, in that case, is 2.6 centimeters. Now, if I wanted to model this, model the oscillation up and down, then, so let's go with brainwashing, y being up and down. Y as a function of time is equal to my amplitude, 2.6 centimeters, or 0.026 meters, times a trig function times my omega, which we calculated to be, that's what we want, so. Radians per second, that's an 11. That's just a straight mark. That's 5. What trig function should I use?
Cosine,
Why cosine or not sine?
because it doesn't start from the equilibrium.
If you are starting from 0, sine is the better way of going. If you're starting from the amplitude, whatever the maximum value is, starting from cosine. Now, the question is, do we want up or down to be positive in our model? because I pulled it down. So so I either starting at negative 2.6 or I'm starting at positive 2.6, but it determines what we're considering positive or negative, matters. So let's just assume up is positive, so negative. This would be the function that models it. Assuming 0 is at a position of 38.6 centimeters. So it could just do plus 38.6 centimeters.
I have a question.
Yes.
I feel like, maybe I'm just confused. I feel like we've done a lot of moving from meters back to centimeters, and I'm confused on how that's gonna give us, like, why would we not use meters in this equation?
Because I was lazy. 0.026 meters, cosine of 11.467 radians per second times time, plus 0.2366 meters. I know that the cosine of this whole bit right here has no units. Cosine, all the trig functions are just ratios of lengths. So this bit right here with the cosine is unitless, and so the units of my first term is going to be whatever my units here are. And I just made sure that that was in the same units as that. So either one, perfectly fine.
Okay. So it doesn't necessarily really matter.
No. Typically, it's good to be in meters, but I'm not really going to manipulate this at the moment. Other questions? Steady boy, steady.